Hi all. This is going to be the lecture 4 of chapter 1 of Numerical Linear Algebra series based on the book by Trefton Lloyd. So in this lecture we are going to see about the overall view of the singular value decompositions. So singular value decomposition is a kind of a matrix factorizations where we factor given matrices into two or three matrices. So what if we take a SVD on a general matrix M cross N? So we now can see as a based on a geometrical perspective, it is some kind of a transformation. A transformation of what? A transformation of units a sphere, which the image we are getting by this transformation is a hyperellipse. So what is hyperellipse? The hyperellipse is nothing but normal. We see an ellipse in a two-dimensional space which have a principal axis like a major axis and minor axis. Similarly, a hyperellipse is an ellipse in an n-dimensional space. It's a generalization of a two-dimensional Euclidean space. So this m-dimensional space hyperellipse have m axis similar to like two axes in an Euclidean space. It has m axis and the m axis in m orthogonal directions from u to m, and the length that length of the each axis is possibly sigma 1 to sigma m, and sigma I and ui is combined like since it's an unit vector and sigma I is the length what we define, then sigma ui is the principal semi-axis of the hyperellipse with length sigma 1 to sigma m. What if a has reduced rank like r? It means that only the r values of sigma I is equal to 1 to r will turn out to be a non-zero. So if a matrix is m cross n and m possibly a greater than n, then at most n of them will be the non-zero values. So we told that there will be a image transformation from an m-dimensional space n-dimensional space to the n-dimensional space by mapping of a, and this is what the geometrical perspective, and S is assumed to be like an unit sphere in an n-dimensional space which has like a equal axis like v1 to vn, and because of that acting of that mapping a matrix m cross n, it turned out to be that a the resultant matrix as will turn out to be an hyperellipse with major that hyper that axis will be defined by sigma 1 u1 to sigma 2 u2 to sigma n un at most. So this is going to be the geometrical perspective. So now we have so far assumed that a has a full rank. Later we will try to relax that. So so now we will define based on this geometrical perspective what are the properties of a in terms of this shape of as. So it means that it's a hyperellipse. It has the matrix a has n singular values. So n singular values from sigma 1 to sigma n. We know that what does it mean by sigma 1 to sigma in terms of geometrical perspective is nothing but the each one is defining the length of the axis, principal semi-axis of the AS. And we are also assuming that sigma 1 to sigma n are being ordered in a descending order. Then again we coming into the u 1 to un are termed to be as a left singular vectors of a. It is nothing but the direction of the principal semi-axis of that hyperellipse defined here as a as. So thus the vector sigma ui is the ith largest principal axis of the as. So what does mean by V? We want to be in nothing but a right singular vectors of A. In this is where the matrix acts in order to get the hyperellipse AS. So it is like a pre-images of the principal semi-axis, and this is also numbered from V1 to Vn. So here you see from this perspective this seems to be in the right side and this is to, but this is termed to be as a left singular vector and this termed to be right singular vectors, but that can be addressed through interchanging here and there are somewhere, but this is what the terminology is all about. That's what it says in the book. and this is what defined as not like a full SVD, it's like a reduced, it's called as a reduced SVD because the rank and the reason for it is because it's a matrix, this is a vector equations and it's termed to be as a matrix equations, and this is what the simpler notation is all about. And u is of size of m cross n, and only n maximum of orthonormal columns are formed by the m cross n matrices, and it's not a unitary matrices, and v is a n cross n matrices, and sigma the singular values are in the diagonal values, and this is a diagonal matrix of n cross n, and this is a pictorial representation of the reduced SVD, so m cross n, it's not a square matrix, this is a square matrix n cross n, and this again and square matrix n cross n for the reduction. What about the full SVD? So we told earlier that it's an m cross n matrix and it's not unitary matrices. To order to make a transformation to unitary matrices, we order arbitrarily m minus n some orthonormal columns to this matrices, so that u had become u, and it will be like a square matrix of m cross m. In order to compensate that, we will add another some m minus uh, n rows into the diagonal matrices, so that it will be multiplied with that redundant m minus n columns to have this m cross n. So this will be added into that, and these are some of the redundant information added to have the full SVD for full rank matrices. So what about if we have a rank division matrices like n, and the rank of the matrices not necessary to be n, uh, it can be some arbitrary value or. So on that aspect is still the full SVD can be composed based on the reduced SVD. Only in this instant what we have to do is n may be a larger than r. So what we have to do is instead of n we substitute r, so m minus r columns will be added here and m minus r rows will be added here. So this, because of this compensation, here we will add additional n minus r arbitrary orthonormal columns to the matrix V, so that it becomes a full SVD. So only the if it is a rank division, there will be an additional addition of the n minus r orthonormal columns here. So this is going to be the standard definition for the singular value decomposition of the matrix. The formal definition is it's as mentioned in the beginning of the lecture. It's a matrix factorizations which we have, and it's a unitary matrices. And this is going to be another unitary matrices and itemize and diagonal matrices with the utmost n non-zero values. So if it is a rank division, it can be arbitrarily r non-zero values. So if we not again here m not necessary to be larger than n. If in sense whatever n is larger than n, it can be also a fatty matrices where sigma 1 to sigma n greater than 0 will based on minimum of m comma n. So the formal definition is that unitary map V is like a pre-imaged one is it will represent a sphere, and diagonal will is going to be the diagonal matrices, and the singular value is going to represent the length of the hyperaxis where with that matrix transformation into a hyperellipse. Then again the u holding that columns holding the directions where the unitary sphere in an n-dimensional space is stretched in order to form the hyperellipse. So this is going to be an important theorem based on for the SVD. One good thing is for every matrices m cross n has a singular value decompositions. Furthermore, these singular values are uniquely determined, and if A is a square and the sigma j are distinct, the left and right singular matrices are uniquely determined up to complex signs. So it means that every matrices can be decomposed to be a singular singular value decomposition has a matrix factorizations of singular, and this will be an unitary matrices called left singular vectors, and this is going to have diagonal entries of singular values. At most value in the non-zero value, a number of non-zero value depends upon the rank of the matrix. uh, uh, and we also going to be a unitary matrices where in a geometrical perspective it will be acting as a unitary sphere in an n-dimensional space, and u is going to be a hyper where the transformation ends up in hyperellipse is going to be represent the axis, semi-axis for that transformed hyperellipse, and the length of the axis will be determined based on the value of the non-singular values embedded in this diagonal matrix. Hopefully we'll come up with the next video on the SVD in the next video. Thank you.